So I believe you all have, just a moment. I believe you all have the way to access to Avenue to Learn. Usually for the course materials and the homework assignment, the announcement, I will all post them on Avenue to Learn. So it will be able for you to access during the whole term. And for this class, the class is it's called a travel demand analysis. It's a focus on the transporting planning topics. In the class, I will introduce some theoretical knowledges about the transporting planning, and also I do some modifications from the previous year's experience and introduce more practice for you to use the transportation related softwares, including Amazon, the Queen's OD, and Transcat. So with that, both theoretical understanding about how the transporting planning knowledge is applied, how you're going to use in the software for some practical issues. First of all, the first page shows some of my contact information. The phone number is definitely my office phone, and it's not able for me to access to my office for now. So the best way for you to reach me is to contact me through my email. I've checked my email very frequently, so this will be the most convenient way for you to ask the questions. Of course, you can. I believe you all have already added to the class in Teams. So if you have any other questions, you can also send a message through Teams to me directly, or leave your questions in the Teams channel, and I will go back to check all of them later. And for this class, the lecture is scheduled on Tuesday from 6:30 to 9:30 p.m. This is the default time for all the graduate class in the civil engineering department. But it's set to be changed by the instructors. So that's one thing I will check with all of you later. And the class is actually scheduled as a hybrid meeting. Even without the COVID, it will be the mix of the online and in-person activities. But for this specific situation, for now, from this week until February 7th, they will all be the online lectures. And for this class, it will be different from the other ones. We can keep the class online as long as possible if you prefer it. And also, there will be a lot of lectures about the implementations, the tutorials of the softwares. And for those lectures, they will definitely be online. It will be much easier for you to follow the instructions in the class, as well as using your own computers to do the practice by yourself. So if there's any change about the switching from online to in-person, I will let you know on Avenue to Learn. If there's any notification from Avenue to Learn, we will keep it in MS Teams. So just try to make sure that everyone's safe. I don't know how the university will change the policy later. To be honest, they haven't give us any update about the policy yet. So let's just wait until February to see what kind of changes will be for this class. And if it's an in-person class, it will be scheduled in the engineering building JHE 144. That will be the first floor next to the main entrance of the engineering building. It will be easy for you to find. The MS Teams is the one that you have already applied to join the class. So you can just discard that. And also I schedule an office hour. This is a weekly office hour from 11 to 12 on Tuesday. But if there's any conflict to your current class, to your meetings with your advisors, you can always send me an email to make an additional appointment. So that's for the lecture and office hour. And the regarding to the meeting time, I'm pretty fine about the night time, but I'm not quite sure whether you have any preferences about changing the meeting time to the afternoon. For now, I have the time slot available on Tuesday from 3 to 6 p.m. If you prefer, I can change the time to switch the meeting time from 3 to 4 in the afternoon. If there's any conflict, then we can keep the original time from 6:30 to 9:30. I'll give you some time to consider that, and well, during the break of this lecture or the lecture today, we can have some brief discussion about it. But before we go to that discussion, let me try to finish about the things related to the course outline. So for the format of the class, for now, we have the live lecture sections. It's offered online. And you know that the 3 hours lecture is pretty long. So I will divide the whole lectures into 2 sections. And each section will be around 1 hour and 20 minutes, and there's a 10 minutes break in between. And also, depending on how many questions you have, I will try my best to reserve the period to answer your questions. Usually that could be around 20 minutes Q&A sessions. With that, you can raise your hand to ask your questions, and if you find anything during the lecture, and if I did not see your raising hand, then you can just leave your questions in the meeting chat and say that what your question is and which page is about that question. Start with the page number, and if it's in the general questions about the class, just specify this is the general questions, and I have some questions about the contents, the topics covered about the class, the format of the class, and so on. Or just simply raise your hand. I usually will open 2 computers. One is about one computer is for me to make a presentation. The other one is trying to monitor what kind of questions you have in the meeting chat. So that's what I do. I will try to catch your questions as early as possible. And for the textbook, in this class we do not have any mandatory textbook to be used. There will actually be 2 recommended reading materials. The first one is the modeling transport. This is a very good book to discuss about the topics in transporting planning. The latest edition is in 2011. If you search this one, you can actually borrow the book in our library. And I don't know whether there's any electrical version. If it is, just let me know. You probably can download it online. And the other one is called the Discrete Choice Analysis, the Theory and Applications to Travel Demand. This is kind of an old book. It's also a very good book, but this book will focus on the theories about the discrete choice models as a part of the transporting planning theory. And also the book has, because it's quite a theoretical book, there will be a lot of equations and formulas for you to understand. In this class, we actually will use a lot of materials from these 2 books, but I have already summarized them in the course in the notes. So you don't need to read the whole book. What you need is just following the course materials, the lecture notes, and try to understand the series and also the examples in the lecture. That will be enough for you to get all the knowledge from the class. And of course, there will be some prerequisites, like you need to have some basic knowledge, mathematical knowledge, and know some fundamental calculus, the probability theory, and some statistical analysis knowledges. I will give you a review about the some prerequisites in the next lecture, and also some reading materials will be shared for you to understand what's the preliminary knowledge you have to know. So that's the textbook, and for the assignments and the other activities you need to involve. For the take-home assignment, I will assign 5 homework for the whole term, and it will take about 20% of your final grade. Usually for each homework assignment, there's a fixed deadline. If you need any extension, you have to contact me before the deadline. Otherwise, your submission will be discarded. And also, in order for me to understand your understand how you're gonna learn the course materials during the class, I will design 4 quizzes. This is just a temporary number. It might be more or less. It will take around 10% of your final grade. The quizzes, usually these quizzes are related to the materials delivered in that lecture in that specific day. And it will be some simple questions and quite related to the examples showing the lecture. So if you follow the instructions, it should be easily for you to finish all the quizzes. It's usually the quiz will only take around 10 minutes for you to finish. And we also have the midterm exam. The midterm exam takes around 35%. There's a temporary schedule about the midterm exam, but the time might be changed depending on the schedule, the contents, the topics that we covered during the whole term. And also we have the final project. We don't have any final exam. There's the final project. The topics about the final project will be shared with you maybe around one month before the final week. So we have the 1 month to work on the final project. And this is the tentative schedule for the whole class. We have 13 weeks, and in the schedule you can find out what we're going to cover for each week and what's the approximate time for me to assign the homeworks. Just remember that this is the tentative schedule. It's not finalized, and it will be changed over the term. Here we will have the topics going to cover it in this class. It's not listed based on with respect to the schedule. Instead, it comes with the what's the materials, what's the contents will be covered. Basically, we will have some series to be introduced related to the travel demand analysis. That will be the economic demand theory, which will try to connect the economic series with the travel demand models. And we are also going to introduce the microeconomic demand theory, and that link this one to the transportation planning of the city or even a larger area. And then we have some introductions about the travel demand modelings, some theoretical models to conduct the demand modeling, including the direct modeling and the 4-step models. For the 4-step models, we're going to focus on the first 3 steps: the trip generation, trip distribution, and the discrete choice model. Regarding to the trip assignment, based on my schedule, we may not have enough time to cover all of them. So what I plan is I would like to provide some reading materials for you to finish the last step. And the last thing is about the software. In this class, we're going to learn 3 major transportation softwares. The first one is Amazon Microscope Simulator. This one is some material. It's in the software to conduct the microscopic simulation. And I know that a lot of you are using the simulation for your research, and the Emerson simulator would be a very efficient tool to conduct the transporting simulation. This one is not highly related to the transporting planning, but I still would like to invest one section, one lecture to give you a tutorial about the Emerson simulation. And also, once you know how to use the microscope simulation, you can actually learn the macroscopic or mesoscopic simulation in Emerson by yourself. And those two will be related to the transporting planning. And there's another one is about the Queen's OD. This is a software to tell you how to estimate the OD matrix based on the observed link flow rate. And it could be extended to a large scale network. It can complete the calculation automatically and efficiently. And of course, the last one, the Transcat, is one of the very efficient and commonly applied transporting planning softwares. And well, I plan to reserve several sessions for all these three softwares. And with that, hopefully you can utilize them for your future research. I guess that would be the materials related to our course outline. With that, do you have any questions? Do you have anything you want to ask about the about this class? Okay. Any questions
I have
about?
a question actually.
Yes. Yes.
About the final project, is that gonna be individual project or is it a group project or?
It will be an
I'm
individual
asking.
project. It will be an individual project, and you will give some questions with the standard answers. And also with some open questions. Yeah.
Thanks.
And the final exam will be the final project will be delivered. Will be shared with you like maybe in early or not early, in mid-March or something around 1 month before the final week.
I also have a question. If we have in-class exam, maybe next lecture, could you please like notify us in advance?
Yeah, definitely. Usually I'll give you like 2 weeks notice about when the midterm exam will be. But it might not be exactly the same to the one I show in the schedule. This is kind of tentative schedule, and we need to check our paces depending on the topics that we're going to cover before the midterm exam.
What about in-class quiz?
The in-class quiz will usually be it depends. It depends. Usually for the in-class quiz, I can let you know before the class, because I actually designed multiple quizzes, more than 4 quizzes, and I have to check which one, or based on your homework assignment and your how you work about the homework assignment to see your understanding, and then check whether I need to assign the in-class quiz for the next lecture. Or if you are doing well for one topic, you probably don't need to set up the in-class quiz. If you are not doing well about some topics, and I probably will set more quizzes there.
Okay, thank you.
For the in-class quiz, you don't need to worry about your exact answer. Usually it will be graded based on your attendance, and I will try. The purpose of the in-class quiz is it's designed for me to understand how you're gonna and understand the course materials and how much you learn from the class. And with that, I can adjust the topics or the examples in the future to help you better understand the course.
Okay, I see. Thank you.
Okay. So this is a this here we have the course outline. Those are the information I extract from the course outline, and you might find that it's a little bit different from the document, the Word document I shared on Avenue to Learn. I actually made some modification before the class today. So for any difference, if you find any difference, just use the one in this lecture as the final standard, the final materials for the course outline. Okay. Okay. So that's the course outline, and now I would like to bring the discussion about the class time. Would you like to change the class time from the night to afternoon or to the morning? And for that, of course, we can try to accommodate the time that you have.
And me personally actually prefer to have a class in the afternoon because my efficiency would be better.
Okay. Okay.
Yeah, for me, afternoon is better.
Yeah, it's I believe everyone prefer to have the afternoon session. It's actually pretty flexible if we hold the if we hold the lecture online, then afternoon and night would be there will be no difference. But if there's any in-person class, then there will be a huge difference. Okay, so if the afternoon works for everyone, then I probably can change the lecture time from 3 to 6 on Tuesday afternoon. So, and if let me know if there's any conflict about your schedule. If there's any conflict, we can definitely change that one to accommodate all the students in the class. Any thought, any ideas about it? Okay. If there's any conflict, I would move the meeting time to Tuesday afternoon, 3 to 6, and I will send an modification announcement on Avenue to Learn so that they can keep everything in record. Okay, so that's pretty much the format of the class. And now for the lecture today, one of the major topics that I'm going to cover is about the some background information and the reason why we want to take this class. And I believe all of you are in the transportation area, and you can see that there will be a lot of challenges for the transportation engineers and for both industries and government, and for the transportation professionals. The purpose of the transportation system is to provide some mobility and some transportation services for all the users in the city or even in the even larger areas. And as the transportation professionals, we not only want to provide a service, we also want to provide high quality services with a low delay. And we also want to monitor the congestion information in the road to reduce the environmental impact, minimize the emissions, the hazard air pollutant emissions, to reduce the risk of the collisions, make sure that you're going to safe on the roads. So those would be the key challenges of the transport system. And in the developing countries, well, these problems will be even more severe, and because they are growing very rapidly, but they have limited resources, and their planning will have some, because with regard to the transporting studies, you need to have the planning about the network, and this kind of limited resource will restrict the amount of the road that it can build, and the with that, you're going to have the limited accessibilities to a lot of areas in the city or in the country. So the quality of the transport services in the developing country will be even lower. And for the worldwide, the safety is one of the important issue we have to consider for the transport study. You see that every year there will be around 1.2 million fatalities caused by the car accidents, and more than 10 million people are injured, and the financial loss could be more than 520 billions. This is a very huge loss, and it will have a significant society impact to all the countries in the world. So this is a very challenging issue. So transporting is a very challenging topic that we need to think about for the government and for the industries and academia. To understand the transportation problems, we have to know two important trends which can affect the transportation studies. The first one is the globalization. So you will know that for all the countries nowadays, for all the countries across the world, they have the tighter connections with each other, and there's a greater economic integrations. The one products can be produced in one country and assembled in another country and then sell in the third country or even more countries. So that requires a lot of transportation services from one country to the other one. And the other things about the other trend is about the better telecommunication technologies. With that, the people will have better understanding about the demand and the supply from different regions. So they need, with this kind of advantages, you can plan the supply chain and having a better planning about the transporting logistics about all the products. And even for delivering the people in the city, you will have the more efficient method to deliver them. So these two trends will bring the challenges to the transport system. It can also bring the potential innovative solutions to the transporting services. Another thing that we have to consider is like the development of the electronics can help to solve a lot of transporting problems. That will include the computing technologies, the wireless communication technologies, the electrical vehicles, and so on. So those will bring the new transporting mode to help us minimize to achieve the net zero emissions in the city, to help us develop the safer transporting mode or the innovative transporting mode such as the shared rides and the multimodal transporting system. But all those things will bring some challenges for the transporting planners in the city. You know that with more variables introduced, the system will be more complicated. So for the transporting planner, they will have more work to do. For this class, definitely we will not go directly to that target. Instead, we will start from the beginning. We will learn as someone without any knowledges in transportation area. So one typical problem we're going to solve in this class is like for example, let's just talking about a city, and they have some budget to develop the road, to build a new road, or to do some upgrade about existing roads. And the city may or the board of the city may give you a question, why you want to build a new highway in the city? And as the planner, you need to explain to them why you do this. And the simple answer is like the transporting planning models tells us to do this. From the transporting model, we can gain this kind of benefit. We can bring this kind of mobility services to the city to reduce certain amount of congestions and so on. So here, the model is the key part, like how we're going to model the transporting services in the city, and how we're going to try to make the model accurate and reliable. it's the major task that we have to do as the transportation planner. Usually for the travel demand modeling, we need to think about 4 questions. The first one is why do we model the travel demand? Why we want to include the number of the trips in your model, and what's the benefit? What's the model can tell us? And the second is like how do we model the travel demand? What's the tools we can use? And the third one is who will use the model output. We don't want to generate a bunch of the data and get a set of the findings and no one going to use it. That's not the case. And the third thing is like we want to have the big picture. As the transportation planner, usually we're going to consider a city on the very large metropolitan area. We are not focus on the individual behaviors like how vehicle is moving on the road, how the signal is set. Instead, we're going to focus on how the traffic services, the transportation services, it is in the city. So those would be the 4 questions we have to think about as the planner to use the travel demand models. Oh, I see there's one question. Yeah.
Dr. Young, since my research is mainly focused on freight transportation,
yes.
Would you please highlight any differences in demand modeling for freight transportation and passenger transportation, if any exists?
Yes. There will be a lot of difference. First of all, usually about the freight transportation, it will be related to the for the freight transportation, usually will relate to the products instead of the people. So the patterns, I mean the demand and the supply patterns will be very different. For the passengers, they will have the purpose about the trip, like they gonna go to work, they gonna go to school, or they go to some entertainments. While for the freight, it's usually about the related to the supply chain, like what's the demand of these products in this area, and what this kind of supply, this demand is related to the potential demand of the residents or the industries they're gonna use about these products. So that's one. The other thing is about the other major difference. It's about the mode they're gonna apply. Usually for most of the logistics, it will be related to the truck and also maybe the train. So the behaviors of the trucks and the passenger cars will be very different. Usually the selections of the routes and the individual dynamics of the trucks and the passenger cars will be very different. So those would be the 2 major differences about the passenger cars and the freight transportation. But they can all be put in the transportation planning models as long as you follow all the necessary components for the planning. Like you need to specify the demand and supply, and you can specify the mode for you to satisfy the demand and supply, and then they can all fit into the model. So regarding to the model itself, there's no difference, but there are some difference about what kind of model going to use, what kind of the demand and the supply would be like for the 2 different modes. Okay. Any other questions? Okay. If no, then we're going to jump to the next page. So for the transportation planning, here I will just go through them some contents to give you the brief introduction about the travel demand models. First, give you some introduction about what is the travel models, and then how to build a model, and then followed by the 4-step model, which is a very popular models applies for the transport planning, and the model output, the performance metrics, which would be the one for you to use the results. And the last thing is about the potential applications for the model. First of all, it's about what is the model. Usually the model, if you go to check Wikipedia about what's the model, and model is defined as a simplification of the reality. Usually know that the realistic problem is very complicated. There will be a lot of factors you have to consider. But for our models, we cannot consider all these factors. So we need to make some simplification. And then this simplification will only focus on the some most important factors. And you can just use these factors to understand and analyze the problem you want to study. Like for the transportation, if you want to study the congestion, you want to see what's the amount of the vehicles will enter in this area, what's the distributions of the road geometry, what's the features of the road, what's the percentage of different type of the vehicles, and so on. And in this class, we will rely on some mathematical models. There will be some clear benefit about the mathematical models. These models will have some equations, and also with these equations, we can have some replicated key features of the transport system, or the behaviors of different road users. And we can, with the mathematical models, we can clarify the assumptions and allow the objective discussions about the problem. So we can always reproduce the results. And if you have the same input, you will have the same output. And also the models will allow you to calibrate some models, calibrate some parameters, and allow you to learn through the experiments to improve your accuracy of the results, and to represent the real world situation. And of course, you're going to allow the replication. So with multiple simulations, multiple models, with same input, you will always get the same output. But also they have some drawbacks. First of all, for most of the mathematical models, they would be the problem specific. Like for the some models that you develop for one city, it's probably not easy for you to extend to another city, or even to another town of that city, of the same city. And the other drawbacks that is to develop a model, it might require a lot of data for you to calibrate the parameters. And sometimes if you extend the model to a large city, it might be very complicated. If the simulation, the model of the Hamilton and the model of the Toronto will have very huge difference. It's you probably can run a simulation of the Hamilton traffic in some simulators, but on the other side, you probably cannot do the simulation for the Toronto network. So this is the difficulty will increase exponentially depending on the size of the network. So that's the definitions of the model. But in our class, we focus on the traffic models. So usually for the traffic model, it's defined as the computer program which can run the mathematical equations using the input data to replicate the travel choices of the individual users. So with the traffic model, we can identify the what's the origin, what's the destination of one trip, and how the route of the trip is selected, which road you're going to take in the network. And for the traffic model, the output will usually be a measure of the future travel demand. And usually we're going to use the volumes of the link volumes to represent the the performance of the network. So with the model, as I say that with the model, you can try to represent the current traffic condition, and then by predicting the future demand, you're gonna model what the future network looks like. If you want to see the congestion, you can see that by increasing the demand about 10%, what's the additional congestion will be generated in the city, like in 5 years, in 10 years, or even in 20 years. So usually for the traffic model, it's kind of simplification for you to understand to predict the future travel behaviors, and we're gonna predict where the people will travel to and travel from. We're gonna predict which route the people will choose to drive from their origin to their destination. And so that's what we do about the traffic models. And also we have to know why the models are important in transportation area. First of all, the model would be the heart of the transportation planning. As you can see from the first picture, you need to rely on the model to let other know what's the why you make this decision. And the other things like the other benefits like the model can help you to understand the long range transportation plan. Usually for the transportation planning, we are focused on the understanding the transportation system for at least 5 years, 10 years, 20 years, or even 30 years. You're gonna see how the cities will be developed in 20 or 30 years. And the also can help us determine how much traffic will be on our roadway in the future. So if you don't change your road geometry, you don't add a new road, by increasing the demand, how many vehicles were moving on your current highway, on this current highway, like for Hamilton, how much vehicles will drive on the Skyway road, and in 5 years, in 10 years. If we added a new highway in Hamilton, how much of the vehicles will reroute to that road? And also it can help us to understand the impact that the new development in our transport system, as what I say that about a new highway in Hamilton area. And also it can provide some instructions to spend the future investment. If we want to build a new way, where you can set the new road. If you want to do some upgrades, which road you want to upgrade, and what kind of improvement you want to set for one specific road. So all this can be provided. All this information can be extracted from the model. And I say that the model will allow us to make the informed decision. So all the decisions we made for the investment, for the new construction, will have some data to support. And this data comes from the model. So that's the reason we need to use the model in our transportation study. And the other things we want to cover is what are the travel models used for? Generally, the model will be provided for the decision makers to find out the best possible information about the future needs. Like if we want to make a decision about the construction two roads, but you can only take one, you can use the model to decide which one is better for you to take. And also, the transportation congestion is another important issue. The model can help you determine where the congestion might be happening in the future. With that, you can build a new road or extend more lanes in that area to release the congestion. And that's what they said. The third one is like determining what the project will be alleviate or minimize the congestion. So even for the new road and the upgrades, you can make a comparison whether new highways will help you to solve the problem, or you can save some money with to just upgrade the existing infrastructure to gain the similar objective. And the other thing is about the scenario analysis, which is a what-if analysis. Say that if we build a new road, what's the consequence? If we do the upgrade, what's the consequence? If you upgrade the infrastructures, what's the consequence? What benefit you can get? And also you can use the model to decide how many lanes we are going to set for the road, depending on the demand, the current demand and the future demand. And also we can determine the traffic demand impact due to the land use changes, like the residential area, the business area. If the planning of the city is different in the future, what's their impact? Say that you have the new shopping mall set at one specific areas of the city. They're gonna attract the people to go to the shopping mall, and they will change the patterns of the traffic in the city, and this kind of changes can be revealed by the model. And for the last, it's very important for almost all the transporting projects. So that's some background about why we're going to use the transporting models. And here's one example scenario. For example, if we consider you are the metropolitan planning organization planner or engineer, you have some finite amount of the budget to develop to improve the current transport system. And your job is like you want to decide which, there will be multiple proposals about the roadway projects. Someone proposed that you need to build in the road. I'll say that in Hamilton, you want to build in the road a highway. Someone say that they want to build in a new like a light rail, or someone say that they want to optimize the signal timing plan and so on. You have to make a decision about which one you need to take. And they say that you have limited budget, you have limited resource, and you need to choose the best one from all these proposals. And also the public will drive the road every day. You cannot do the real world test, like if you want to build, you want to close the roads, close one road to do some construction, then it will significantly affect the traffic conditions in the city. And with all these constraints, you need to think about how you're going to select the best option. And that's what we will do, is that we're going to use the travel demand models to determine what's the how we're going to address the existing congestion problems. Like if they have the congestion on this road, probably with the model, if the model tells you that you can just add one lane to this road, then all this congestion is solved. Then it's not necessary for you to construct a new freeway or new road in the city. And usually in the model, we can do some tests, evaluate various proposals. And because it's in the model, it's not in the realistic project. You can test it as much as possible. And using some standard variables, such as the VMT, VHT. VMT is a vehicle mile traveled, VHT is a vehicle hour traveled. To identify the savings of the VMT and the VHT, and of course restricted by your budget, to decide which one can give you the highest benefit, the highest saving. Then you will you're going to select the one with the best performance. So that's some typical work that as the city planner is working on. And the next thing is like if we want to build in the travel demand models, we have to think about where we're going to start. And what we need to start the development. the things like usually for the model development, the most important thing is about data. So without data, you cannot do anything. For the travel demand models, we need to consider a variety type of the data. Like for the transportation planners, we need to think about the population, how many people lived in that area, how many jobs, the employment, how many jobs can be provided, and how many households in that area. The household is more important than the number of the people, and whether there's any school, what's the geometry of the road network in the city. So those would all be the data that we have to collect to build the model. And the next thing is like we have to think about what causes us to travel each day and how we can get there. So that's related to the purpose of the trip and the mode of the trip. So those are all the data we have to collect. But as the transporting planner, you will get a tons of the data, and then you need to find out, or you get the data from all areas of the city, and the amount of data is very large. So you need to think about how you're going to organize data. And in the future, if you want to extract the data for some specific area, you will be able to find out them quickly. And also the data should be organized and be applied, easily applied for the travel demand models. And so before the data is collected, we need to develop the system to organize the data first. So that's the first thing we have to consider. So to organize data, the most common method we applied in transportation system is utilizing the traffic analysis zone. This is the TAZ zone. It's commonly applied for the transportation planning. The whole city will be divided into multiple traffic analysis zones. And usually the traffic analysis zone is defined based on the geographic areas where the data is stored. So this would be the simplest way. It could be usually for the if we are talking about the US and Canada, they will have some census area. In the bureaus of census, they will collect the population, employment, the school enrollment information for each region. That's the region defined by themselves, and we can just using the this census region directly to define the TAZ zones. This will reduce the effort, the data organizing effort a lot. And so that's what we're gonna do. We will try to align the TAZ zone with the census geography, and those will be the will contain the could be some aggregated census blocks. Is not in a single community or in a single block of the city. Instead, it might cover multiple communities or multiple blocks, depending on the density of the population, the density of the employment or the school district. And this would be one example about the TAZ zone of the city. And you can see that, well, here there will be approximately 91 TAZ zones, less than 100 TAZ zones for the whole city. And you can see that inside the city, the TAZ zones will be much smaller because usually the density in that area will be much higher, and the census zone will be smaller compared with the suburban area where the density and the residents will be much low. And the absolute area may not be matters, but if we have the region with the similar density, then probably the TAZ zone will have similar size. This is just one example. We will have more discussions about the TAZ zones in the future lectures. This is for now, we will just have some brief introductions about it. For the TAZ characters, usually they will have they will approximately equal in size, but not the absolute land areas. They usually will be smaller in downtown area, but larger in the suburban area. And for each TAZ zone, they will represent the homogeneous land use. It could be, if it's in the residential area, that will be all the people there will be the residents. And if it's the business area, there will be the some companies, some shopping malls, and so on. For the boundaries of the TAZ zones, they could be usually we will choose the roadways. So it would be the arterial roads, the freeways, and so on. And also, the TAZ zones will typically follow the census geography. So the could be single blocks depending on the definition of the census zone or the group of the blocks. And the goal of the division for the TAZ zone is like we want to replicate the areas of the origin and destination. So usually the people, if it's the depending on the purpose of the trip, like for the people, if the TAZ zone is only designed for the residential area, the people exiting the zone will usually be the home-based trip. So they can come to the school, they can come to go to the work, or go to some entertainments. If for some business TAZ zone, they will attract a lot of employees in that area. So that's the reason we want to have the make some divisions about the zone. You can easily for us to capture the origin and destination of the trips and identify their purpose. And for then, once we have specified the TAZ zones, we need to identify what kind of data we need to collect for the transportation planning for the travel demand models. The first type of data we need to collect is the socio-economic data. This data is very important because the travel demand models actually comes from the microeconomic demand theory. Those ones are highly related to the economic data. So the typical data will include the population, the household unit, the household size, how many people in each household, what's the distributions of the household size, the employments, the school enrollments, the vehicle ownership is another important factor. We need to know how many cars is owned by each household, and the income levels apparently affect the number of the trips. Also, the land use characteristics, the business area, residential area, or some entertainment region. So this would be the socio-economic data. This is one typical example. One example about the socio-economic data. You can collect the data for the columns will shows different type of the data, and the rows will shows the different type of the zones that you collect for the whole region. It's one example about the previous figure about the division of the TAZ zones. So for example, for zone 5, you can get the zone 5 is not a good example. Zone 6, you have the total number of population of 949. You get the occupied dwelling units, so which would be the household as 343, and you have the retail employment 316, the total employment 434, and so on. So those would be the information you need to collect for each zone, each TAZ zone that is specified. And now with the socioeconomic data, we can then try to identify, to estimate how many of the trips can be generated in each zone. And this is called the trip generation. Usually to determine number of the trips, we have to using some linear regression models or some statistical models to determine the the number of the trips generated for each zone in a typical day, like weekdays or weekends, they will be different. This will need some surveying data to conduct the model, the trip generation model. Again, for the first lecture, I will not go through too many details about how the trip generation model it looks like. We will have some specific lectures to discuss about the trip generation step. And for the transporting planning, we're gonna focus on 4 steps. That's the most commonly applied models. We have trip generation to tell you how many trips will be generated. We have trip distribution to tell you where the trip will going to from one origin to one destination. And the third one is the mode choice, about what kind of mode you're going to take. Whether you're going to take the public transit, you drive your own car, take the train, or you walk by yourself, or bike by yourself, and so on. And the last one is the trip assignment. You have this step to identify which path they're going to take, whether they're going to take all the local roads, whether they're going to take the freeways, or the combinations of local and freeways. So for now, let's go to see some more details about the 4 steps. In the first step, trip generation, we're going to determine how many trips will be produced from one TSZ zone, or will be attracted to one TSZ zone. So you can see the figure here. We have 3 TSZ zones. One is the home, the other one is the employment, and the third one is the store. With the trip generation analysis, we can determine how many trips is generated from the home, and for the employment, we can identify how many trips they can attract to enter this region. And similarly, can find out the definitions for the stores. Of course, there will be more details we're going to cover in the future. And for the trip generation methods, in this class, we're going to cover the cross classification method. They're going to use this one. Will use to determine the trip production by each TSZ zone, and it's usually related to the number of the people, the size of the household, the car ownership, and so on. And we can also use the trip rate based on the activity units. There will be some, actually there's a manual provided by the IT trip generation manual. It can tell you how the trip is estimated based on the activity, whether they want to go to the hospital, they want to go to the school, go to some fast food restaurant and other entertainment area. And the commonly applied methods for the trip generation is called the regression equations, which is kind of the statistical models. They're gonna collect some, do some surveys, gather a sample of the trip rate with respect to the socioeconomic data, and apply the regression models to estimate the trip production and trip attraction in each TSZ zone. And I say that this is based on the real-world observed data. And also there will be some other specific trip generation models. This would usually be some independent model applied for some specific trip purpose. For example, the trip to the hospitals, the trip to the university, to the regional mall, the military base. They will have very different trend to the trip where people need to have the daily commute. For example, for the university, it's very different from the people who need to take the trip to their office. Like for the university, the trip might be highly related to the schedule of the class start time of different years of the students. Like the patterns will be very different, totally depending on how many students are enrolled in each class, and what's the start time of that class, and what's the end time of the class. So it's very different from the majority of the passenger trips. And the other thing related to the trip generation model is about the trip purpose. Usually the trip purpose can be identified as the home-based work, where the trip will start from the home, what is between the home and the work. And also the home-based others is the trip between the home and the other place. And now home-based trip, which would be the trip that does not involve the home in the destination, in the origin or the destination. And some external trips, which would be trip from some region outside of the network or the trip exiting the network to the other areas. We will have more details about the definition when we're going to introduce the trip generation models. And with the trip generation model, we're going to get the trip production and trip attraction. The production indicates how many trips will depart from this area. And trip attraction means how many trips will enter this area. And this kind of production and attraction is identified based on the TAZ zones, as well as the purpose of the trip. So we will identify how many of the trip will leave this area, and what's the portion of them will be the home-based trip, what's the portion of them will be the home-based, not home-based trip, and so on. And the second step is the trip distribution. So from the first step, you know how many trips will be generated by one zone and how many trips will be attracted by another zone. But we don't know how many trips will leave one zone and enter another zone. And that's what we want to do in the second step, the trip distribution. Usually for the to identify trip distribution, the first thing we need to do is define. First thing we need to do is like we have to define the road network. We need to know the geometry of the road network. And you know that the for the TAZ zone, it's an area, and we assume that all the trips will be generated from that zone. And this means that we need to specify the one location for us to generate the trips in the model. And that required us to identify the centroid for each zone. This is the same figure from the previous example about the TAZ zone definition. And in this zone, each green star represents one centroid. It indicates that all the trips will leave the zone from that point, or they will enter the zone at that point. So for the definitions of the network, we have to consider nodes, the links, the centroid for the transport system. The node will represent the intersection of the link, will represent where the road segment starts, where the road ends. So you should specify the two ends. That's the node. The link will represent the street or the road, the freeways. It could be the local road. It could also be the highways. But at most of the time, the minor road will not be modeled in the transport demand models, because those would be very small and usually will be inside of the TAZ zone. And the centroid is just one specific location, as we just explained in the previous page, as one location which can generate a trip, which can attract the trip, and that will be specified as the origin or the destination for your trip. And the third thing would the last one is the centroid connector. It will be in the virtual link from the centroid to the net to the other links to the actual roads in the roadway network. And later on, I'm going to show you one figure about the links, node, centroid, and the centroid connector. But before that, we also want to go through some network attributors. To model the network, we want to know the speed, or we want to know the speed limit of the link. We have to know the capacity. What's the maximum amount of the flow that the road can support? What's the directions of the road, and the travel time? What's the free flow travel time? If there's a vehicle loaded there, what's the travel time? What's the relationship between travel time and flow? And the functional classification, whether it's road only supported the passenger cars, whether it's a road only supported it's only available for the bus, or whether it's in carpool lanes and so on. And the traffic counts, how many vehicles moving on the road. This is one example about the network the network development, how we're going to construct a network. All the black lines represent the actual road in reality. So the single black lines represent the major roads, the major local roads, and the thinner lines represent the some residential roads, or the some service roads, which would be the minor roads. The blue region is one TAZ zone. Apparently, if you want to model this all these roads in your model all the road all the lines in your network, it will be very complicated. So for the transportation planning models, we will try to make some simplification. Instead of using all the minor roads, we just using one centroid, which would be the square in this figure, to represent where the trip will be generated, and where the if the trip will enter this centroid, how it will at which location it will be ended. And in the for the other major roads, we will still keep them. So the thicker black lines will still be reserved for the network, and we will remove all the minor roads and build a connector from the centroid to the major road. So in this case, you can see there will be 3 connectors. They are not the actual road. Instead, it will be some virtual roads. It will just connect the centroid to the actual roadway. So you have 3 rows, 46 to the node, 300 and 138, 46 to 140, 46 and to 142. And so these 3 will be the centroid connector. And you can also see these squares, not the square, the circles. That would be the nodes applied for the to represent the construction of the network. And for any lines between 2 nodes, that will be the link. And of course, we have the network attributes. We have network attributes for each link. So that's the way for us to develop the network. And this would be the more complicated case. We have for the previous example, for the previous complicated example, we have 91 TAZ zone defined, and with that we have 91 centroid. And you can also see the yellow lines that will represent the links from the centroid and represent the actual road. And also the blue lines will represent the boundaries, and usually that will be the roadway we're gonna use for the the actual roadway in reality. And I guess it's a 7:50 now. So let's take a break for 10 minutes, and we're gonna resume the meeting at 8:05. Okay, and in the meanwhile, if you have any questions, well, just let me know.
Dion, I have a question.
Yes.
So I have a question that how many the connectors do we need? Do we need to connect the central to just like every boundary? That's like you show in the
not necessary. It's usually the number of the connectors is usually defined. It's the number is usually selected pretty arbitrarily. It depending on the shape of the TAZ zones, the size of the TAZ zones, and also the accessibility of the TAZ zones. For example, from here, apparently you don't have any link the actual minor road connect from the centroid to this major road directly, right?
Yeah.
So you do not have any connector to this road.
Yeah.
But you can find out there will be some connectors, some minor roads from the TAZ zone exiting to the major road for all the other three directions you are going to have. With that, you have specified the centroid connector. But also it depends on the volumes that are applied in this minor road. If you see that this minor road does not have a lot of vehicles traveling there, then probably you can just discard the centroid connector to this major road. It's a pretty option and also case by case, as there isn't any standards about the identifying the centroid connector.
Yeah, and I think we can say the selection of the connectors or the location of the central is. It sounds like something that is subjective in some ways.
Because you know that if you add a more centroid connector, your model will be more complicated.
Yeah.
And this is what we have to find out the balance between the complexity and the accuracy.
All right. And the location of the centroid, it should be the at where? I mean, it must be the central of the TAZ zone or any location within the zone.
Usually, it will be the center of the TAZ zone, but you need to remember that for the centroid connector, it does not have any physical meanings. Those would be the virtual line. It does not have physical meanings. It does not have the actual distance, the actual speed, or the capacity. The vehicles exiting the centroid were directly loaded to the network through the node 138. So it doesn't matter. It doesn't matter.
There's no so strict issues.
Yes. Just tell. It matters about how many connectors.
Yeah.
But it does not matter about what's the length of the connectors it looks in the network.
Yeah, I see that. Thank you.
Yeah. Okay, so there's another question from slide 38. What does the green object symbolized? Or the green represented river? I did not specify just a river. Yeah, so it's some obstacles that it cannot pass. Okay, so I'm gonna turn off my camera and just wait until 8:05 to resume the lecture. Okay, let's resume the lecture. So, well, I guess. So for now, once we have developed the network, then we can then use the network, the identified centroids, to define the number of the trips departed from one region, from one TSZ zone to another TSZ zone, which would be the trip distribution. This is here is just one example. We have said that we are working about the 3 zones. Zone 1, we know how many vehicles were entering, and how many vehicles were exiting the zone. So P represents the production, which means that the trip will be generated. That will be 20, and A represents the attractive, how many vehicles, how many trips will enter the zone 1. It's 200. Also, you can find out the production attraction for zone 2 and zone 3. So those would be the information we estimated from the trip generation step. And now we need to identify how many trips from 1 to 2, from 1 to 3, and 2 to 3, and backwards. So the purpose of the trip distribution is just determine where trips are going to and coming from. And usually we for most of the travel demand models, we're going to apply the gravity model. In this class, we will also learn the gravity model from the theories to the implementations, including the calibrations of the gravity model for the trip distribution. This gravity model is kind of the analogous of the newest law of degradation, and it will try to maximize the one utility function. The core ideas like the number of the trips between the zones will be directly proportional to number of the productions at the origin zone and the attractions at the destination zone. So basically, we can use the equation listed here to calculate the number of the trips from zone I to zone J, and PI is the production from the zone I, and AJ is the attraction from the zone J, and also we can find out the Fij and the Kij will represent the frictions and the cost from zone I to zone J. You don't need to know the details about how these equations is generated. We will not work on this topic for now. It will be covered in our future lectures. Just give you some brief ideas about what the gravity model looks like. And this is the friction factor, and there will be some typical friction factors. Usually the friction factor is inversely proportional to the travel time from one zone to another zone. With the longer travel time, the friction factor would be smaller. And usually for the trip distribution, we have to consider the cost, the travel time, which will be usually measured with the which will represent the cost from one zone to another one. The cost can be estimated based on the shortest path from one zone to another one. And with that, we need to identify the shortest path for all the zones, which we call the scheme trees for the transporting planning. And for the Transcat or the OD matrix or Amazon, they will have the tools to generate the scheme trees directly, automatically, so you don't need to calculate it by yourself. Of course, you will have the multiple ways to do it by hand if it's in a small network. And here is one example about the trip distribution. Again, I will not go through the details about how we're going to use that one, but you can see the you can use an example to see how we can find out the trip, how we calculate trips. Like for example, for the trips traveling inside of the zone 1, the number of the trips is depending on the productions and attractions. The production is 20, attractions 200, and also you can find out the friction factor. For zone 1 it's 3.6, for zone 2 it's 2.5, and the zone 3 is 2.0, and then you can calculate the number of the trips inside of zone 1 is 13, and from 1 to 2 it's 2, and with that from 1 to 3, that will be 5, something like that. We're gonna give you more details about the estimation of the friction factor and the implementation of the gravity models later. So here's just one example. With the trip distribution model, we can then identify the number of trips from for any one zone to the other zone. For this specific example with 3 zones, you can find out the trip matrix from zone 1 to 1, 13, 1 to 2 is 2, 1 to 3 is 5. You can also find out the trip from 2 to 1 is 143, 2 to 2 is 51, 2 to 3 and 106, and so on. So that's the output of the trip distribution. And if we go to check the complicated problem in the previous examples in previous city, we can identify the very large matrix, which will give you the trip distribution from all the 91 zones to the other 91 zones, to all the other zones. Again, it's impossible for you to do the calculation by your hand, so we have to rely on the some softwares, and Transcat would be one commonly applied software, which we will learn almost the end of this class. And I'm also going to show you in the class, I'm also going to show you how to use the Transcat to generate the trips, how to use the generated trip to estimate the number of trips from each origin to each destination. That will be the second step, and the third one is called the model split or the mode choice. Once you have specified the number of the trips from, say that from zone 1 to zone 2, you will, as an individual individual road user, you need to decide what kind of mode you're going to use, whether you're going to drive your own car or whether you're going to take the bus. So that's what we need to do in the third step. And usually for the selections of the or for the choice of the transportation mode, this one is very important as for the planner, especially for the public planner. For the planner in the public agency, they have a lot of effort spent on encouraging road users to use the public transit system so that they can reduce the congestion, to achieve the goal of minimizing the air pollutant emissions and so on. So it's very important for us to understand how people will select the mode. And the fact is that for the buses, they will be more efficient, and because the capacity of the bus is pretty high, much higher than the passenger cars. And the train will have even higher capacity, so they can better transport the passengers. Subways and trains will have similar benefit. They can help to alleviate the congestion. And while we see a lot of drawbacks of the cars, the car will require a lot of parking spots, and it's a major cause of the congestion on the roads. But the one of the key advantages for the park is like it's convenient. It's very easy, flexible for you to use. You can take your car at any time. You can identify your destinations by yourself, and also compared with the bus, usually will move much faster, and also you can take a lot of personal items in the car. So those advantages still makes that the passenger car is the most popular mode for people to use. Even though the government is still trying to apply various policies to encourage people using the public transit. So that's the fact we have. And now in the third step, in the mode split, we need to quantify their advantages and disadvantages of different modes, the bus, train, subways, and also the cars. And then using the quantified values to identify what kind of percentage of the trips will use the car, what's the percentage of them will use the public transit modes. So the that's what we that's what we're going to do in the third step. And also as we say that the mode choice is very important for the urban transportation efficiency, and it's a major task of the most of the public transit agency, and it's also benefit to the environment. And the mode choice is also important for the intercity travels, especially for the long distance travel. And now from the second step, we know how many trips are moving from one zone to another zone. And the next thing we need to identify how many of them will use the public transit, how many of them will use their own car. And that's to solve this one, we're going to use the discrete choice model. And again, this one will also be introduced in the future lectures. I'm just give you some information about why we need this mode choice. And the last thing we want to work with is if we know how many people are traveling from one region to another one, we know the mode is going to take. Say that it's going to take your car. The last thing we're missing is what kind of route you're going to take. Like for this example, you have an origin, you have a destination, and you have multiple options for you to drive from the origin to the destination. This kind of purple line is just one potential route. You can also select another route, taking the horizontal line and then vertical line directly to your destination. You also have the other options to take the route to your destination. And in the last step about the traffic assignment, we need to determine how many trips will use this route and how many of them will use the other route. And if you have more than 2 options, what's the percentage? How you're going to distribute the trips to all these options? And that's what we need to do about the trip assignment. And there will be multiple ways for us to do the assignment. If the road is not congested, usually the people will only choose the one with the shortest path. That could be the one with the shortest distance or the smallest travel time. Or the second method could be the human behaviors, related to human behaviors. There could be some stochastic models based on the habits of the human drivers, like they do some survey and check what's the percentage of the people who are using Route 1, what's the percentage of using Route 2, and so on. Just apply these statistical values. And the third one is related to congestion. So they have some capacity constraints. Like if one road is very congested, then the people might switch to the other roads to avoid congestion. Something about that. And the last thing, which is also the most commonly applied method is the equilibrium. So it assumes that all the drivers, all the passengers on the road are selfish. They always try to find out the shortest path. They're always trying to find out the route with the smallest travel time for themselves. So eventually, for all the trips from origin to destination, no matter what kind of route they're going to take, their cost will be the same, and which means that they're going to reach to the equilibrium. So that's the last method, and is also it's also true for the real world situation. People will choose the one which will be the best, have the best performance for themselves instead of the entire system. So the for the past trip, for the planning of the trip of the pass, we will need to consider the travel time. That's in order for us to find out the equilibrium, we need to consider the travel time or the friction factor. As you see that the friction factor is the inverse of the travel time, and the congestion or the congestion level, or we use the volume capacity ratio to represent congestion level. And the third one is the turning penalties or the prohibitions. This one is related to the intersections. Well, usually for the left turns, they may experience the slower speed compared with the through traffic, or they may the left turn signals will be usually have less or shorter green time compared with the through time. So there will be some penalties applied for the turns. For the left turn, usually we're gonna welcome. For the design, we usually assign 50 seconds penalty for left turn, and for right turn, we will assume that it will be the same with the through traffic. So those would be the factors we need to consider for the planning of the pass to determine the cost of the pass, and then identify the equilibrium. And the link volumes and the speed is also applied for us to estimate the travel time of each link. And the turning movements at intersection will be related to the turning penalties. And also for the entire model, we want to estimate the regional vehicle mile traveled or the vehicle hour traveled to see what's the performance of the entire network. And also there's one congestion measurement for the network instead of the link. We also going to use the volume capacity ratio to identify the congestion level. And if you go to check the highway capacity manual, which is developed by the US Federal Highway Administration, they will identify the congestion levels from A to F, and it's related to the volume capacity ratio and the speed of the link, and so on. There will be several definitions there. And for another thing that we want to, once we finish the models, for the first step models, we run the simulation. Another one output we want to summarize for the network is called the network volume. We want to identify what's the volumes of each link. Like this is one example that you can see. For each link, you can see the volumes, the number of the vehicles traveling in that link per unit time. For example, for this one, for this link, it's pretty small, but you can see the value is around 1,514, something like that. You can, if you have the transcat, you can use the different colors to represent the volume. You can use in the red color to show that there's high volume, the green to represent there's less volume. Also, you can get some equivalent variables using the average speed of the link, or the average density of the link. So this is the one typical output from the transcat. if we're using different thickness of the line to represent the volumes, the thicker indicates that it's have the higher traffic, and it's the thinner represent that it has low traffic. With that, you can clearly see that how at which region is more congested, and which region will be easily cause the congestion issues for the entire network. So with that, we have the constructed model, and that's not the end for the job of the transportation planners. There will be some other things that we have to work. Once you have developed a model, you need to validate the model and try to identify whether there's any potential errors from the model, because it's quite common that you made some errors for the network building and for the estimations of the production, and to identify the mode used for different trips. So to get a reliable model, we will need to first do some estimation to estimate the parameters of each link. What's the speed limit? What's the capacity? And what's the critical density, and so on. And then we need to calibrate the model to make sure that all the parameters that we estimated in the first step are consistent with the data we collected in reality. And once you have the model calibrated, you're going to run the simulation. You need to validate with the observed traffic count, and to show that whether the congestion pattern you modeled in the network is consistent with the observation, whether the flow you simulated in the model is similar to the one you observed from various sensors installed on the road. And with that, once you find that from the validation the model is accurate enough, then you can apply the model for the different planning projects, so that you can try to double check using the model to simulate how the congestion looks like in the next 20 years. For example, if you have the model about Hamilton, and you find that you do some calibration and validation about the model, and you find that the model is pretty accurate to capture the congestion at the year 2021. And now you can try to do some predictions about the increase of the populations in Hamilton, say that Hamilton has 550,000 population for now, but say that in 20 years it will increase to 800,000. Then you can use the 800,000 to predict what's the total number of the trips will be generated in the city, and then predict what's the congestion looks like in 20 years, in 2040 to 41. And that will give you a better sense about which road is very critical for you to improve, whether you need to add a new lane, or whether you need to build a new highway to alleviate the congestion. Another thing that we need to, two additional things we need to do is about the reasonableness check. For some models, even though you see that all the volumes that you find is consistent, but if you find that there's some region, for example, for some minor road you observe in very high volumes, probably means that the model is not correct, or you need to specify some restrictions for that minor road. This is some common sense. We need to remove all this unreasonable scenario, and also we have to make some sensitivity check. That will be related to the reliability of the model. We need to, for example, we need to make a increase or decrease the demand a little bit to check whether the simulation is still reliable. If your model is reliable, like you make a smaller change about the amount of the trip you modeled, you may observe a totally different congestion information. And if that happens, means that you need to adjust some parameters of the model. Otherwise, your predictions about the future traffic is not accurate. So the here we will have some details about the model estimation and the rest of the steps. For the model estimation, we will actually use, most time we're going to use the statistical estimation about the model parameters, especially about the trip generation model. At that step, we will apply a lot of linear regressions to the trip generation. And we are using the statistical estimation to identify the trip length frequency distribution and try to make sure that it's consistent. And for the calibration, we will try to using the existing observed parameter, observed flow or the observed trips to calibrate the parameters, make sure that it's able to fit to the observed data. And the validation is majorly focused on the traffic count, try to make sure that we can capture the flow and the congestion levels in the model. And the application is checking the reasonableness of the future year traffic and also the identify whether it's sensitive to any demand changes or any policy changes. One last thing I would like to include for the introduction is about the a comparison about the potential implementations of the travel demand models. Say that we have two models. For the implementation, we will usually consider the base year model and the future year forecast year model, which could be like 10 years, 20 years, or 30 years later. And for the base year model, we want to do the calibration to make sure that it matches to the observation, and it can reproduce the existing congestion information. And we can, once we make sure we calibrate this model and validate the model, we can then we will be confident that this model is true, it's accurate, and it could be applied for the future year traffic transportation system analysis. And then for the forecast year, for most of the public agency, we want to do the transport planning for at least 20 years or even longer, 30, 50 years. And we're gonna for the forecast, we're gonna focus on the socio-economic data instead of the transporting data itself. Say that we're gonna focus on what's the population changes from the current year to 20 years later, 30 years later, or even longer. What's the employment opportunities, and using this socio-economic data to predict the total number of the trip will be generated and attracted for the city. And also for the future years, the city may have the new road built, and this new road could be included in the future year network. And then we're gonna run the run the model to see the traffic conditions in the future year. But for the analysis, we will not only work on the base year and the future year directly. We will also check what happens in between. So we will try to identify the traffic conditions for some interim year scenarios. Say that if we want to work on the planning for the year 20, after 20 years, we want to check the base year, which would be the current situation, the traffic condition in 5 years, in 10 years, 15 years, and then 20 years. We will then see the gradually change of the traffic conditions over these 20 years. And that will give us a better sense about how the traffic, how we should introduce the new construction project, how the population and employment changes will affect the transportation services in the city. So that's the implementation. We will basically need to consider the two models, but the intermediate interim year scenarios should also be investigated. And here we will have some typical scenarios for the implementation of the transporting models. Say that what if no improvement will be done for the for example for Hamilton Road, what happens about the transport services in 20 years? The model can tell us. And we have some congestions, say that in the main street for year 2020, but this congestion might be different due to the redistributions of the population, the residential area, or the constructions of the new shopping malls. Might be the other roads like the highway 403 will become even more congested, but the main street will be less congested, something like that. And the second scenario is like, what if a new mall is proposed to a new location in Hamilton area? It might attract a lot of people to go to that mall. For example, if the new mall will be constructed near the McMaster campus, probably the students at McMaster will never go to the downtown Hamilton, will never go to Ancaster for shopping. Instead, we just stay in the West Hamilton, stay around the Hamilton area, around the McMaster University. And this will significantly change the traffic patterns and congested regions in Hamilton. And say that another example is that if we build a new bypass around the northeast side of the Hamilton area, and or if we see that the toll road 407 is free in the future, how you gonna change the congestion information on the QEW in the next 5 years, 10 years, 20 years, and so on. And also say that if we have 30 new road constructions in the Toronto area, and but you only have 15, you have the budget for 15 of them, how are we gonna select the best 15 projects through the 30 proposals? And that's also related to the transportation planning, how to build a reliable travel demand models for the current year and the future years. So all this will be the potential implementations of the travel demand models. And in this class, we're gonna introduce the fundamental knowledges about how to conduct the travel demand models. What's the insight of those models? For example, for the four-step model, for the travel trip generations, why we want to choose the linear regression model, how we're going to use the linear regression model, how we're going to calibrate the parameters, and how the trip generation model is linked to the trip distribution model. What's the mathematical insights of the trip distribution model, and so on. So these fundamental knowledges will be covered in this class. Of course, there will be some examples and some practice will be distributed for you to implement, for you to get familiar about the those fundamental knowledges, the theoretical knowledges. But we will get in touch about all those details in the future lectures. I guess that will be all about the lecture today. So as this is the first lecture, so I will try to make it short. So with that, I will conclude the lecture today. And after this lecture, I will collect the recorded video and upload the video on Avenue to Learn. But before I leave the meeting, do you have any questions? And again, for this lecture, for the first lecture, it's just the introduction. I know there will be a lot of details I haven't covered, but it just gives you some sense about what's the basic ideas of the transport planning, and we will go through all the detailed knowledges, all the detailed topics in the future lectures. Okay. Do you have any questions?
I do have a question.
Yes. Yes.
So on slide 46.
For the 43? Yes.
46.
Oh, 46.
Yes, sorry.
Yes.
Yeah, I'm not sure if I'm guessing wrong, but I just assume that the sum of the column would be equal to the total trip attraction.
Yeah, if we do the sum about the each column, it should be the same to the attraction, but there will be different methods for the trip distribution. We will learn them later. There will be production constraint distribution, trip distribution models, the attraction constraint distribution models, or the double constraint distribution models. This one is only about the production constraint. So you only make the total production consistent with all the zones. But if you do the summarize all the values in each column, you can get an attraction. It's not necessarily consistent with the attraction because this model is not the attraction constraint model. If it's an attraction constraint, then yeah, it should have the same value. Yeah.
Okay, that makes sense.
Yeah,
thank you.
we will have the introduction about all the models, the production constraint, attraction constraint, double constraint with the cost, and so on. You will have all the ideas about how to use them, how to distribute the trip to each cell in this matrix.
Perfect. Thank you.
Okay. Good. That's yeah. Good.
So, I mean, if we do the model validation, so how can we do the validation for the forecast model or the interim model?
We do not do the validation for the forecast years. For interim year, also not for interim years. We only do the calibration for current year or
For the base model.
Yeah, only for the base model. And once the validation is done and the validation satisfy our requirement, we assume that this model is good, and we can then apply this model for all the forecast years. So that's one key assumption for the transportation planning models.
Yeah, so we conduct our forecast model based on our base model.
Yes. Because for the future years, we have no idea about what the trip looks like.
Yeah, we just know the population and employment.
Yeah, and even for the population and employment information, it's still a kind of the prediction.
Yeah.
It's not accurate. We can only give them some basic ideas about what the future looks like, but it's not 100% sure.
Okay, it makes sense. Thank you.
Okay. Any other questions? Okay. If we don't have any questions, that will be all. Again, as I said, that if you have any questions, just send me email. If you have any concerns about the class, send me email. I will give you a reply as early as possible. Okay, that's great.
So our next course will at 3 p.m., right?
Yeah, will be 3 to 6 on Tuesday.
Okay.
I will send you an announcement on Every to Learn so everyone can keep in track about the change.
Okay.
Okay. I guess that will be all. Thank you very much, everyone, for joining the lecture, and I will see you next week.
Thank you so much.
Thank you so much.
Thank you. See you.
Bye.
Bye.